Hello, welcome back to HECJ Academy, where we entertain you with fun animated science videos and actual academic tutorials. Today, we will be crushing isotonic and buffer solutions in pharmaceutical calculations. The key concepts and formulas will be made very easy and exercises will be solved. Now, let's get right into the video. For illustration purposes, let's say you have a container holding a particular liquid, and then you divide this liquid into two parts by introducing a semi-permeable membrane in the middle. The expectation is that there will be no overall net diffusion of the liquid from the left to the right side or vice versa, because the osmotic pressure on both sides are essentially equal. Now, when you introduce some particles of a substance to the left side and osmotic pressure builds up there, liquids diffuse from the right side to the left side. The process by which this liquid moves across the membrane from right to left is called osmosis, and the factor responsible for this movement is called osmotic pressure. In this illustration, the left side is said to be hypertonic, that is, it has relatively high concentration of the solute, while the right side is said to be hypotonic. So diffusion of the liquid goes from the hypotonic region to the hypertonic region. Osmotic pressure increases with the concentration of the solute. So the more solute you add to the left, the more hypertonic it becomes and the more osmotic pressure it generates. Now, there are some substances called electrolytes that break into ions when you dissolve them in a liquid. For example, sodium chloride ionizes into sodium and chloride ions. Just take it that the tendency for sodium chloride to break into these ions when dissolved is called the degree of dissociation. You see, when it breaks, just one sodium chloride particle will yield two particles in the solution, hence adding to the osmotic pressure. We will discuss this in more details when we treat milliequivalents and milliosmoles. So, for electrolytes, osmotic pressure is affected by both concentration and degree of dissociation. For non-electrolytes, it is only affected by concentration. Hope it's clear. Let's continue. Generally, there are some properties that are affected by the number of particles of a substance in solution. These properties are called colligative properties, and they include osmotic pressure, vapor pressure, boiling point, and freezing point. When you change one of these properties, there are concurrent changes in the other ones. This is important because sometimes we can easily determine the osmotic pressure of a solution just by determining the freezing point because they are related. Two solutions that have the same osmotic pressure are said to be isoosmotic. Now, if somehow you are able to prepare a solution that has the same osmotic pressure as a natural body fluid, like tears for example, that solution is said to be isotonic. If that your solution has higher osmotic pressure than the body fluid, it is said to be hypertonic. If lower, it is said to be hypotonic. Hypertonic solutions, when introduced to a body cavity, will likely draw fluid out from that body area, while hypotonic solutions will likely push fluid into that body area. Generally, drugs that are meant to be used in the eye, nose, and bowel are expected to be isotonic so that there will be no significant loss or introduction of fluid in the body structures. This may cause discomfort or even harm the patient. However, if the goal is to extract fluid from that body part, hypertonic solutions can be used. For example, in edematous tissues where there is an unusual fluid accumulation in the body, hypertonic solutions will help drag out that fluid. Apart from making the solution isotonic, we also use buffers to maintain the pH of that solution to reduce irritation as well. There are some important facts and figures we must get used to in order to be able to solve any question on this topic. We will go over them now. Minus 0.52 degrees C is accepted as the freezing point of blood serum and lacrimal fluid. Hence, any solution that freezes at this temperature is assumed to be isotonic. When you dissolve 1 molecular weight in grams of a non-electrolyte in 1000 grams of water, you will get a solution with a freezing point of minus 1.86 degrees C. So, when you compare this minus 1.86 with minus 0.52, which is the freezing point for an isotonic solution, you can easily cross-multiply to know how many grams of that substance you will dissolve in 1000 grams of water to get an isotonic solution. Let us illustrate this with boric acid, which has a molecular weight of 61.8 grams. When we dissolve 61.8 grams of boric acid in 1000 grams of water, we get a solution that freezes at minus 1.86 degrees C. Now, how many grams of boric acid should we dissolve in 1000 grams of water to get a solution that freezes at minus 0.52 degrees C? 1000 grams of water is constant, so we can cross multiply the extremes to get x times minus 1.86 is equal to 61.8 times minus 0.52. On cross multiplying, we get our final answer to be x equal to 17.3 grams. The implication of this is that if you want to prepare an isotonic solution of boric acid, simply weigh 17.3 grams of boric acid and dissolve in 1000 grams of water. Note that 1000 grams of water is the same as 1000 ml because the specific gravity of water is assumed to be 1. Remember, this formula only holds for non-electrolytes alone. For electrolytes, we will have one molecular weight in grams dissolved in 1000 grams of water to freeze at minus 1.86 times I. I is the dissociation factor of the electrolyte. Let me show you how it is calculated. For example, when particles of an electrolyte like sodium chloride go into solution, a percentage of that sodium chloride will dissociate into sodium and chloride ions. The other percentage will remain as sodium chloride. It is accepted that NaCl generally dissociates by 80%, so 80% will break into sodium ion and chloride ion, while 20% will remain as sodium chloride. To calculate I, or dissociation factor, let us assume that we introduced 100 particles of sodium chloride. Inside this 100, 20 particles will remain as sodium chloride. 80 particles will each break into sodium ion and chloride ion, giving us a total of 80 sodium ions and 80 chloride ions. So in the end, we have 20 sodium chloride particles plus 80 sodium ion particles plus 80 chloride ion particles, giving us a total of 180 particles. Since we started with 100 particles, I, or dissociation factor, is equal to 180 particles all over 100 particles, which is equal to 1.8. In fact, we assume the dissociation factor values to be as seen in the text below. Sodium chloride dissociates into two ions, sodium and chloride, so it has a value of 1.8. We can use the other values for other types of electrolytes as required. Another important fact we must remember is that a 0.9% solution of sodium chloride is isotonic. This means that it has the same osmotic pressure as the normal body fluid like blood serum and lacrimal fluid. This also means that it freezes at approximately minus 0.52 degrees C. Let me demonstrate how this value was arrived at. The molecular weight of sodium chloride is 58.5 grams. The dissociation factor of sodium chloride is 1.8. Therefore, 58.5 grams sodium chloride, when dissolved in 1000 grams of water, will freeze at minus 1.86 degrees C times 1.8, which is the I factor. Now, how many grams of sodium chloride should we dissolve in 1000 grams of water to freeze at minus 0.52 degrees C? We cross multiply to get that x times minus 1.86 times 1.8 is equal to 58.5 grams times minus 0.52. When we cross multiply, we get that x is equal to 9 grams. Hence, 9 grams of sodium chloride in 1000 ml of water is isotonic. To convert this to percentage, 9 grams sodium chloride was dissolved in 1000 ml. Then how many grams sodium chloride is present in 100 ml? We cross multiply to get 0.9 grams, which is 0.9%. Finally, let's talk about sodium chloride equivalent, also called E-value. Then we may proceed to solving exercises. So far, we have seen how to calculate the quantity of any drug to dissolve in water in order to obtain an isotonic solution. However, we cannot always dissolve that much quantity of drug in solution because it may not be cost effective and in fact may be dangerous depending on how toxic the drug is. Most times we are asked to only dissolve the appropriate dose of the drug in the solution, then use another substance, usually sodium chloride, to make the solution isotonic. So basically, we have to calculate how many grams of sodium chloride we must add to the solution already containing the required dose of the main drug in order to make the overall solution isotonic. So, what do? We start from what we know. 0.9% sodium chloride solutions are isotonic. This means that in every 100 ml of that solution, you will find a total of 0.9 grams of sodium chloride. Now, let us say that we want to prepare 100 ml of drug X and make it isotonic. Adding 0.9 grams of drug S to 100 ml of the solvent will not necessarily make the solution isotonic because drug X is different from sodium chloride. It has its own quantity that should be added to 100 ml to make an isotonic solution. Now, we need to know the amount of sodium chloride that contributes the same osmotic pressure as 1 gram of drug X. To illustrate, if you bring an isotonic solution of drug S and then remove 1 gram of drug X from that solution is no longer isotonic because it has lost the osmotic pressure contributed by that 1 gram that you removed. Now, how many grams of sodium chloride should be added to that solution to be able to replace that 1 gram of drug X that was removed and make the solution isotonic again? This is what is referred to as sodium chloride equivalent, or E value of drug X. So basically, the E value of drug X is the grams of sodium chloride that can be replaced by 1 gram of drug X in terms of osmotic pressure. So, since 0.9 gram of sodium chloride in 100 ml is isotonic, when we add a dose of the drug to 100 ml of pure solvent, we can easily calculate how much sodium chloride is already contributed by that dose of the drug in that 100 ml. Then we will know how many more grams of sodium chloride should be added to make it up to the required 0.9 gram necessary to make the solution isotonic. There is a standard table of E values for various popular substances in pharmacy. We can look up the E values of specific substances and use them in our calculations. There is also a way to manually calculate the E value for a given drug substance. If we encounter such while solving exercises, we will handle it. In the next part of this topic, we will look at freezing points calculations and buffer solutions, then solve some exercises and the case in point. Remember to drop your questions in the comment box if you have one. That is it for today's video. Don't forget to smash the like and the subscribe buttons to encourage us to continue making more contents like this. Tell us what you think about the video in the comments box and share the video if you think it will be beneficial to your network. Thank you very much and bye.